So we are going to build on what we have learned so far about dimensional analysis, using conversion factors, setting up units to cancel out and give a desired unit. We're going to add another layer to that, which is something called stoichiometry. And essentially what this is we are going to be using chemical equations now that we've learned about them. And we're going to use the relationships that we have in chemical equations in order to essentially, instead of just converting, like, let's say from mass to moles of one thing, we can go from moles of one thing, so moles of a reactant, to moles of a product. So essentially now we can go from, let's say, if we're calling like this A, and this B, we can go from A to B. And let's say we're starting off like with the mass of A, then we can go to moles of A, and then from there we can use the stoichiometric relationship to get to moles of B, and then we can go wherever we need. So these relationships from the chemical equation are obviously from the coefficients, but these coefficients can either mean, like if you're looking at it very, like if you zoomed in and you could see the two molecules of CH18 reacting with 25 molecules of O2. It can be that, or it can be more macroscopically, which is moles, but either way it's a ratio, so you can just think of it that way. It's a ratio of how many reactants to products. So just to give you another example, and this is something like more applicable or something that you see very often in your daily life, is a recipe. So honestly, any recipe that tells you like the ratio of what to add in order to get your final dish, that's essentially like, it's the equivalent of a chemical equation, right? So here we have a pizza recipe. 1 crust plus 5 ounce tomato sauce plus 2 cups cheese gives us 1 pizza. So we can express this as a ratio, like with the little colon. And let's say that we had 10 cups of cheese and we wanted to see what is the max amount of pizzas that we can make? How many pizzas can we make? You would set up just the same way that we've been doing with dimensional analysis. You would set this up where we have our given unit, and then given unit at the bottom along with it cancels out. This is our desired unit, right? And the ratio that we used was the cheese to the pizza. So 2 cups cheese equals 1 pizza. And then what we get is 5 pizzas from that. So now back to actual molecules. It's the same exact idea for chemical equations. And what we actually call the ratios, so I know I've just been saying ratios, but they're called stoichiometric factors or ratios, whichever one you want to use. But if you hear me say that, you should know that it's coming from the coefficients in the balanced chemical equation. So we're going to do an example where we are going to start off with the mass, and then we need to essentially get to the mass of a different part of the equation. So this problem is asking for the mass of sodium hydroxide that would be required to produce 16 grams of magnesium hydroxide following this reaction. So I don't have the mole map here specifically on this page, but if you have it like printed, just remember to use it right now. That's what I'm going based off of. So we're starting off with a mass, right? And then we need to go to moles. Well, actually, we're starting off with mass of magnesium hydroxide. So we need to go to moles of magnesium hydroxide. Then after moles of magnesium hydroxide, we need to go to mole of NaOH. And then from there, mass. That's pretty much it. First, we need to figure out our stoichiometric factor, and based off the coefficients here, and this equation is balanced. You should always check it, but I know this one's balanced, so just for the sake of time, 1 mole of magnesium hydroxide is produced from 2 mole of NaOH being reacted. So like I said, we're following this plan. So we're going to start off with our mass of magnesium hydroxide, which is 16 grams. From here, I'm going to set up my molar mass, and I have them up here. So if you didn't have them, then you just need to calculate them using the periodic table. But just to save time, I have them up here already ready. So obviously the mass goes at the bottom. And then on top is 1 mole. Okay, so now we got grams out of the way. So now we're at moles of magnesium hydroxide. Now we need to get to moles of NaOH. And for this, we are going to use our stoichiometric factor. So 1 mole magnesium hydroxide reacts from, like it's formed from 2 mole of NaOH. And next I'm just going to set up the molar mass of NaOH, and then we're pretty much done. So then moles of NaOH cancels out, and then we end up with grams of NaOH, which is exactly what is being asked for grams. Whoops, sorry, right here, grams. And then what we get is 24, let's see how many sig figs. It should just be 2, so actually that's it, 24 grams of NaOH as our answer. So remember we started off with that tiny little mole map, just like with volume and mass and number of atoms. Now we have a giant like web essentially, and this is just to show you how stoichiometry ties into all of this and how it's just what we've learned so far with stoichiometric factors like joining the two. So this is what we've learned so far, right? We've know how to convert from moles to volume, moles to mass, moles to numbers of particles, whatever it may be. All we're doing is we're going from moles of one thing to moles of another using stoichiometric factors. So stoichiometry is like that junction between more than one thing, and specifically it's from chemical reactions, chemical equations. So far we've learned that stoichiometric factors can allow us to determine how much product we make, to determine how much reactant we needed in order to form a certain amount of product. We can go whichever way we want. But in actual life, like when you react something, obviously you need those at least two reactants, and you're going to have a certain amount of each of them, right? When you react them, you're going to find that one of them will run out first, and that is going to limit the reaction. So in order to further illustrate this concept to you, I want to bring back our pizza recipe. And let's say in the fridge, for some reason, you had a bunch of ingredients to make a ton of pizzas. You have 4 crusts, 10 cups of cheese, and 15-ounce tomato sauce. And you want to determine like the max amount of pizzas. Like you want to maximize all the food you can possibly make from this. So you're trying to figure out how many pizzas can we make. So based off the stoichiometric factors, you determine, you set up all your dimensional analysis, right? So for the crusts, you have 4 crusts, it takes 1 crust per pizza, so you end up getting 4 pizzas, right? From that. From cheese, you have 10 cups, and we find that we can get 5 total pizzas from all these cups. And then for tomato sauce, we find that we can only get 3 pizzas max from all this tomato sauce before it runs out. So when you compare all of these 3, we find that one gives us less product, right, out of the ingredients. This is because our reactant is our limiting reactant. This reactant is our limiting reactant. So it's going to run out first before the other things run out. The crust and the cheese, there's going to be some leftover, right? But the limiting reactant runs out completely. And that's what determines how much product you make. So if you had all of these ingredients, the max amount of pizzas you can make is 3. So as our pizza problem demonstrated, the reactant that runs out first or limits the amount of product is called the limiting reactant. We also say reagent. It will get completely consumed in order to form all of that product. And then you'll have other things in excess, and those are called excess reactants. So in the previous problem, our crust and our cheese would have been in excess, so you would have had some leftover. The amount of product that you can potentially get from that limiting reactant, so remember the 3 pizzas, that was our theoretical yield right here. And I wanted to show you just a quick example of how this would actually look like with atoms and molecules, not just pizzas. So here we have this reaction, right? H2 reacting with Cl2 to give us HCl, 2HCl. And here we have 6 hydrogen molecules and 4 chlorine molecules. So the green ones are the chlorines, and then these are the hydrogens. When they react, we find that we get some HCl's, like for example, this is HCl, 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 a bunch of HCl's, and then we find that we get some leftover hydrogen. So in this case, our hydrogen is in excess, so you'll see me often abbreviate excess with an X and an S, and then for limiting reactant, it was our chlorine, because that one is no longer like present. It got completely used up. So let's say that while you were making the pizzas, you burned a pizza. So a lot of things went wrong. You burned a pizza, you dropped one on the floor, or some other thing happened, and you only ended up making 2 pizzas, right? This is your actual product. This is the actual amount that you got from all of this, essentially the reaction. So we can determine like what our yield is or what the efficiency is of your reaction, and let's say for this case pizzas, by calculating something called percent yield. So our actual yield we found was only 2 pizzas, even though theoretically we could have made a full 3 from those ingredients. So we divide those two numbers out, multiply by 100, and we get 67% as our percent yield. So for like chemical reactions and actual problems, you'll be given an actual yield usually. You'll have to calculate that theoretical yield using the information you have, the chemical equation, stoichiometric factors, and then you divide those two out and multiply it by 100 to get a percent yield. So we are going to do a problem where we find the limiting reactant and then we find the percent yield. So it is a bit lengthy, but this will show you the complete process. Now bear in mind, since we're advancing more, and I hope you guys are getting used to dimensional analysis, converting to moles, all of those things, I may not be as detailed as I once was. I'm just going to go ahead and show you the work. But keep in mind, you still keep doing the steps you do. You still double check everything. Still keep those habits. So first, we are going to do this part of the problem. What is limiting reactant when we have 2 grams of silicon reacting with 1.5 grams of N2? So first and foremost, let's get this out the way. What is the molar mass of silicon? And then what is the molar mass of N2? So I got the molar masses, and now I can go ahead and get started. From there, so I'm going to first convert these masses to moles, and then we're going to use the stoichiometric factors to get to the amount of product. So I'm going to set these up. So this was just plain old simple converting to moles from a mass, and we use the molar mass, right? Now is the part where this is like how we convert to limiting, this is how we determine limiting reactant. So for both of these, you are going to do a little test, just in the same way where we had all the ingredients of the pizza and we determined how many pizzas we could get from those ingredients. We're going to do the same thing here. So here we are going to set up our stoichiometric factors. So for silicon to the product, it's 3 mole of silicon. So I'm just looking at the equation, right? And then obviously 1 mole forms 1 mole of silicon nitride. Okay, and then for this one, it's 2 moles of nitrogen gas react to form 1 mole of the product. Whoops. So I went ahead and calculated these out, and we find that this is a very close test. So for our silicon, we get 0.023 mole silicon nitride. For our nitrogen, we have 0.026. So from this one is smaller, which tells us that silicon is our limiting reactant. So our limiting reactant is silicon. That's our first answer. Now we need to determine what our theoretical yield is in grams. So we're going to convert these moles. This is our theoretical yield. We're going to convert this to grams, and then we're going to divide those out, multiply by 100, and we get our percent yield. So next we are going to determine what our percent yield was. So we're going to take our theoretical yield, convert it to mass, and then we're going to divide our actual yield by that theoretical yield in mass, multiply by 100, and then we'll get our percent. So I went ahead and set up this molar mass. So this is the molar mass of silicon nitride. I just added up the masses from the periodic table. And then I set this up and we got our theoretical yield here. And this is just in grams now. So now we're gonna divide these two out. So our actual yield divided by our theoretical, times it by 100, and then that gives us our percent yield. So you should get 76.3, and I believe this was 3 sig figs, so I'll leave it at those. So essentially from this reaction, our efficiency wasn't that great. You know, you would like to get like closer to 100, but 76% is a pretty good yield. You will find that in like actual life, you know, obviously things are not perfect, so pretty high yields are usually within like 80s and 90s.